Let's continue on with our discussion of titrations. In this example, this is the second point in our titration curve. What we're going to do is start off with our 50 milliliters of 1 molar acetic acid, and to that we will now add 10 milliliters of 1 molar sodium hydroxide. And now we'll need to calculate the pH of this mixture. We start, as always, by writing the list of major species that you have in this solution before any acid-base reactions happen. That helps you to keep focused on what's going on and how we're going to proceed in solving this problem. All right, so we have here is acetic acid. That's a weak acid, so you have to keep it together. We've added sodium hydroxide to it now, and sodium hydroxide is a strong base, so you have to break it up. Na plus in hydroxide, and water is always present in any aqueous solution. Now, what you're going to do is look at the list of major species that you have, and in looking at it, you notice the presence of hydroxide ion. This is your top priority when you're looking at the list of major species. Do you have H plus or hydroxide? Because if you see either one of those present, they're going to react immediately and to completion. So the hydroxide ion is going to react with the strongest acid that you have in your solution, which is acetic acid. This reaction will go to completion. Let's write out that reaction. We did that a little earlier when we considered the net ionic equation for the reaction that occurs during the titration. We have CH3, COOH reacting with hydroxide to completion to make the acetate ion and water. And because this is a reaction that goes to completion, this is a stoichiometry problem. For a stoichiometry problem, we're going to do the stoichiometry by making a before, during, and after reaction table. That will allow us to solve this limiting reactant problem in the quickest and most efficient way. So we'll set that up on the next slide. We'll write the reaction again, and then set up the table. Okay, now let's plug in what we have before the reaction occurs. Don't forget that when you make one of these tables, you must do everything in moles. So let's make a note of that up here. Moles. So to find the moles, we'll have to multiply molarity by volume. For the acetic acid, we have that it's 50 milliliters of a 1 molar acetic acid solution. So 50 milliliters is our volume, 0.05 liters, and 1 molar acetic acid, so 1 mole of acetic acid per liter. What we have is 0.05 moles of acetic acid. For the hydroxide, that comes from the 10 milliliters of 1 molar sodium hydroxide that you used. So the volume from the hydroxide, that's 10 milliliters or 0.01 liters. And the concentration of the sodium hydroxide is 1 molar, so 1 mole per liter. So we have 0.01 moles of hydroxide. Acetate ion is not a major species initially, so we'll have 0 moles of that initially, and don't care about water. Next thing for us to do is to determine which of the two reactants is limiting. This is a 1-to-1 mole ratio, and so whichever reactant we have the least amount of, that's the limiting reactant. The hydroxide ion is the limiting reactant. All of it gets consumed, and so there will be nothing left over for the hydroxide ion. Therefore, you consume 0.01 moles of hydroxide ion. And you also, due to the 1-to-1 mole ratio, consume 0.01 moles of acetic acid, and you make 0.01 moles of the acetate ion. When you add it all up, combine everything together, what you find is you'll have 0.04 moles of acetic acid left over, and you'll have made 0.01 moles of the acetate ion. So that brings us to the end of the before, during, and after table. That brings us to the end of the stoichiometry part of this problem, but we're not done yet, because after you complete the stoichiometry, now what we have to do is write the list of major species that remain in your solution. Every time you do one of the before, during, and after reaction tables, you always have to reevaluate the list of major species in your solution, because that list of major species changes every single time you make one of these tables. Let's start by looking again at what were the major species before the reaction occurred. Initially, we had acetic acid, we had Na+, we had the hydroxide ion, and we had water. So from this list, what we recognize is acetic acid. Some of that was still left over, and so that's still going to be left on the list. Na plus was a spectator, so that's still going to be present. The hydroxide ion was the limiting reactant, right? We see that here. The hydroxide ion was the limiting reactant, so that's off the list. And then water is always present as a major species. So in writing the list, we still had some acetic acid left over, so that's still there. Na plus was just a spectator, so it's still there. Hydroxide was completely used up, so that's off the list. Water is always present. And then one more question that you want to ask yourself is, did you make something new that didn't previously exist in your solution? When you look back at the reaction table, you recognize that although you initially did not have any acetate ion, at the end of the reaction, you now do. You made 0.01 moles, so that gets added to the list. Now, from this point, you can then ask yourself the next question, which is, where do we go next? How do we find the pH? Can we use the Henderson-Hasselbalch equation to find the pH? Think it over and go ahead and put in what you think on this. Having given you a chance to do that, go over the answer together. Remember, if the question is asking, can you use the Henderson-Hasselbalch equation, what that's asking is, do you have a buffer? You have to have both a weak acid and its conjugate base as major species. What we have in this solution is our weak acid in the form of acetic acid, and in the neutralization reaction with sodium hydroxide, we produced acetate ion. So although we did not initially have the conjugate base present as a major species, we now do. We have both HA and A minus as major species, and so yes, this is a buffer. And so, yes, we can use the Henderson-Hasselbalch equation to find the pH. We don't have to bother with doing ice tables or any other crazy things to find the pH. All that's left now is for us to plug the numbers into the Henderson-Hasselbalch equation. So the pH is equal to the pKa of acetic acid. The pKa of acetic acid is a given value. It's on the information page. The pKa of acetic acid is 4.75 plus the log of A minus over HA. A minus is the acetate ion. And remember that you can use either moles or molarity here. For the acetate ion, we have 0.01 moles from the before, during, and after table. Over the weak acid, and so for the acetic acid, we have 0.04 moles of that, so we'll put that number into the Henderson-Hasselbalch equation. When you plug all of this into your calculator, what you end up getting is that the pH of this solution comes out to be 4.15. And there you have it. Just for the sake of completeness, I am going to write the Henderson-Hasselbalch equation here, just so that you see where all these things came from, and you'll have that for your notes. So remember, the pH is the pKa plus the log of A minus, which in this case is the acetate ion, over the weak acid, which is CH3COOH. All right, just so that if you're looking back on this, you'll know where the numbers came from here. So that brings us to the end of this example. Next, we'll take a look at what happens after adding 25 milliliters of NaOH.